Welcome to the session on numerics, efficiency, and software. My name is Bernhard Scheider. I'm going to chair this session, and the chair. I'm going to chair this session, and the first speaker is now Matvey Kapushin from the Institute for Systems Programming at the Russian Academy of Science. I think this is going to be a double feature because there will be another gentleman from that institute. Yes, thank you. Please start.
Thank you, Bernhard. Okay, so I'm going to do a presentation about the project which lasted for previous 4 years. It is a joint project of ISP-RAS and Cardiff Institute of Applied Mathematics of Russian Academy of Sciences. My presentation is divided into 5 parts, and first I will give a few words about with introduction, then several words about PIMPLE and PISO algorithm in OpenFOAM, its application. Then I will talk about QGD and QHD algorithms, and then I will show some example of their usage and some examples of their application to several problems. First of all, I hope everyone is familiar with OpenFOAM and other listed computational physics programs like Numerics, Samurai, or even Moose. All these packages are united through such trait as interdisciplinarity. And this trait allows to solve efficiently multiple multi-physics problems within one computational framework. And OpenFOAM uses its own numerical algorithm, which is called PIMPLE. So it's a hybrid algorithm of PISO and simple to solve various complex and multidisciplinary problems like incompressible flows, compressible flows, flows with buoyancy, multi-component, and multi-phase flows. However, this generality comes with some cost. This cost produces restrictions. For example, PIMPLE algorithm is iterative. We need inner and outer iterations at each time step, and this increases computational costs. This algorithm cannot be applied for high Mach number flows. We have to select flux limiters, and also there are some mesh convergence issues. Here I put 4 examples where this algorithm definitely fails. For example, 2 cases are connected with simulation of attractor of internal waves in stratified medium and in toroid, and 1 case is connected with droplet mechanical balance, and 1 case with compressible flows at Mach number larger than 2. So together with Cardiff Institute of Applied Mathematics, we propose to use QGD or regularized equations as an alternative to PIMPLE. Advantages of this algorithm are next. We don't need flux limiters. Numerical schemes are simple and similar for convection and diffusion equations. Monotonic convergence, and they can be implemented in OpenFOAM together with other OpenFOAM models. However, drawbacks are next, computationally more expensive algorithm. So some terms requires approximately 2 to 3 more times to compute derivatives, and this algorithm requires additional stability criteria. The history of the algorithm starts 30 years ago when Professor Chetverushkin derived first version of QGD equations from Boltzmann equations. And during 30 years, this approach evolved for very multi-physics interdisciplinary framework for simulation of MHD equations, porous flows, two-phase flows, and so on. Regularization procedure, which lies at the core of this framework, involves 4 steps. So averaging, substitution with Taylor expansion, substitution of Taylor expansion terms using original equation, and neglection of second order terms. If we apply this procedure to conventional transport equation, we will get additional numerical diffusion term, which is called also regularization term, and this term is a additional smoothness which is added to numerical solution. In the same way, we can apply this regularization procedure, for example, for 1D barotropic compressible gas flow. Here we can see system of equations, and after these steps, we come to regularized system of equations, which looks maybe a little more complex, but at the same time, this system of equations can be approximated with the same and one interpolation scheme. I mean linear interpolation scheme. So approximation becomes much more easier. In this slide, I put again basic steps to derive regularized system of equations. If we compare numerical solution with QHD approach to PISO and simple approach, we can see that algorithm is straightforward. So we have only 4 steps for solution of pressure equation or continuity equation, momentum equations, and 1 step for other transport properties. Instead, in Pimple, we have 1 outer loop, 1 inner loop, and 1 loop to account for non-orthogonal meshes. So the main benefit of QHD and QGD is simplicity of the numerical scheme and numerical algorithm. I think next categories of researchers and engineers can benefit from using QGD. So scientists who want to solve complex set of equations, but they don't want to derive PISO or Godunov type procedure or Riemann solvers. And scientists and researchers who knows how to solve problem with Pimple, but they are not satisfied. They need better approximation. According to this, to stated advantages of and drawbacks of this algorithm, we decided to implement it in OpenFOAM, and after that we made library QGD solver, which includes a small library for approximation of tau terms and several solvers. here you can see two groups of solvers. So one group is foundation solvers, so solvers for compressible gas flow, and one solver for incompressible viscous flow with buoyancy, and several derived solvers for mesh deformation, for flows with particles, and for multi-component and multi-phase flows.
Could you please speed up? You have one more minute of regular speaking.
I see I have a clock.
But there are no questions yet, so you can have some extra minutes. Yeah.
Unchanged. And our solvers were validated and verified on several cases, like T-junction modeling, thanks to Arjun Yadav. It was validated with skew cavity problem, with attractor of internal waves. Here you can see a comparison of solution between NEC 5000, which is spectral limit method on the right side, and on the left side you can see comparison between spectral limit method and conventional PISA solver. We have also validated our solver with two-phase flows, droplet deformation in 3D. Also, we made some simulation with together with Jörn Belke from Dresden. He simulated stratification and instabilities. And also, solvers were used to solve some complex 3D problems like Reynolds 70,000 high-speed jet, interaction of jets and obstacles at high Mach numbers, interaction of jet with liquid droplets and acoustics, and simulation of Kourou spaceport acoustic field, which was performed using QGD solver, Numerics library, and libacoustics library. And instead of closure, I invite everyone who is interested in the process of development to test programs, to collaborate with us, and to join our training track. Thank you.
Well, thank you very much. I think we have 3 minutes for questions. Actually, there have not been any questions typed in yet. People, you can go to the live Q&A box at the right of your browser screen and type in questions there. Until somebody asked a question there is, how much effort is it to port your solvers to new OpenFOAM versions when they come out?
Usually it takes about 2 or 3 weeks to port to new OpenFOAM because we use OpenFOAM Plus, and it doesn't change significantly from version to version. And it takes about 1 or 2 weeks to run all regression tests to check that everything works. So about 1 month.
Okay, I have a question here. The momentum equation from Sergei Lernik, momentum equation is nonlinear in velocity. How do you achieve convergence of both continuity and momentum equation without inner-outer iterations as it is done in Pimple?
It's a good question. In QHD approach, continuity equation is derived directly from, pressure equation is derived directly from continuity equation. And these equations are decoupled from each other. So it is possible to solve them simultaneously, one after another.
Mm-hmm. And 2 short questions. The one is, does the solver work with turbulence? And the other one was about, is there a reference for the derivation and explanation of this approach?
Yes, this solver works with turbulence, and moreover, this framework is intended for transient, non-stationary flows. Regarding the second question, there is a book in English written by Professor Yelizarova, which covers major topics of QGD and QHD approach. This book, I think, is published in Springer, and also there are several articles which were published by me together with Yelizarova, covering topics of QGD and QHD approach implementation in OpenFOAM.
Okay. Yeah, I think thank you very much for your talk. Thank you for answering the question. There's one more question in the Q&A. Maybe we can get back to that later after Mr. Alexander Ivanov spoke, or the person can reach out to you during the conference. Our next speaker, same institute, is Mr. Alexander Ivanov, and he will speak about the development of the new OpenFOAM solver for water simulation using the library that was introduced to us just before. Thank you, and please start.
Yeah, thank you. And should I switch on my camera?
Yes, please do.
Okay. Can you see my presentation now?
We're fine.
Okay, I hope so. Sorry, this is some stuff, a little bit annoying. So good afternoon, dear colleagues. My name is Alexander, and I would like to and I'm an internal researcher of the Institute for System Programming and PhD student of the Cardiff Institute of Applied Mathematics. And this work is the result of this institute's collaboration. So today I would like to tell you about our new OpenFOAM solver, RSWE-FOAM, and so let me introduce it to you step by step. First of all, it is a solver for shallow water simulation, which probably needs a better name because even for me it is difficult to pronounce it. Another point is that it is based on QGD, QHD approach. And the final step, it is a part of the QGD solver framework, which the previous speaker, my colleague Matvey, told you about. So let's go through these points to define what it is and how it works. So as I said, the first point is that it is a solver for shallow water modeling. And as known, the shallow water approximation assumes that the water is incompressible and its depth is sufficiently smaller compared to the wavelength, and the vertical velocities are negligible. So one can use it to model some free-surface problems, for example, tsunami modeling, shallow reservoirs, or lakes, seas, or oceans. On this slide, you can see the shallow water equation system. The designations basically, so H is for thickness of water level, U is for horizontal velocity components, B is for bathymetry, and D is for gravitational acceleration. So the main important property of this system is its similarity to gas dynamic system. And due to this fact, 30 years ago, the numerical solution, the numerical method for solving shallow water equation system was proposed, and it is based on the quasi-gas dynamic method, or QGD. And the main idea of the method is to regularize or average in a small time interval the shallow water equation system and use the regularized system instead of the original one. So the method's main idea, the main steps of the regularization is the next. So firstly, we apply regularization or averaging to the main variables. It is a height or velocity components. Then we substitute them into the equations. Then we apply TLS form for this averaging variables, and here appear time derivatives, which we can again obtain from the original system, and again substitute these expressions into the equations. So by this means we can obtain the regularized shell evacuation system, so RSWE. And you can see this on the slide. The numerical algorithms for solving original shallow water equation system are varied and rather complicated because of the instability of the solution. So, but this system has additional terms in form of second spatial derivatives, which makes the numerical solution more stable. So, and also the regularized system has two important properties. So it is closely related to the original system, and its stationary solution, the stationary solutions of the original system are the stationary solutions for the regularized one. And if we consider tau equals to 0, so the regularized system goes to the original shallow water equation system. And for numerical solving of regularized system, one can use finite area method because it is two-dimensional model. So there is no problem to approximate the right-hand side because it includes the additional terms I mentioned before. So despite the fact that they had so complicated form, as I said, there is no problem to approximate them for some another program. But in case of the OpenFOAM, as I know, there is no convenient tool to approximate. So the problem transformed into two-dimensional case, and in this in the OpenFOAM we don't have convenient tool to approximate spatial derivatives at the cell faces, and here QGD solver framework comes to the rescue. So after that, solver's implementation is very simple because we need to use two libraries, FVSC. It is a basic library for approximation of the spatial derivatives at the faces, cell faces, and we need to develop a new small library to define an expression for tau calculation. So, in this case, the program for numerical solution of shallow water equations, regularized shallow equations, looks something like that. And for example, for continuity equation, the code is rather simple. The structure of the RSWE form case is quite same like the basic OpenFOAM case structure, but here appears a new dictionary, shallow water properties. It includes basic QDD dictionary, which is obligatory for QDD form QDD solver framework, and also it includes parameters and coefficients, like alpha is tuning parameter for tau calculation, and epsilon and flag resonant condition. I will tell you about it later. So let's have a look at several examples. And the first one is the Riemann problem, and the problem statements you can see on the slide. Here the comparison of the basic OpenFOAM solver shallow water form with RSWE form. So one can see that the basic solver has small oscillations here, while the new solver, our solver, is in good agreement with an exact solution. also, there is a so-called dry zones problem in shallow water model. So to solve it, we use special parameter epsilon. It is a cutoff value of water level. So if the water level or water depth is lower than epsilon, we assume that the velocity and tau parameter are equal to 0. And for the dry zone condition demonstration, here we have the same problem like the previous one, but with dry bottom at the right-hand side. So, and here to better approximate, to improve our solution for the velocity, when we can use, we can modify the formula for tau calculation by adding the magnitude of the horizontal velocity. And here you can set it via the shallow water properties dictionary by adding a new parameter tau u, set it to the one constant. So as you can see, the results are quite better than if we switch off this parameter. And so the convergence of the numerical results for velocity and height to the exact solution is demonstrated. And by decreasing epsilon parameter, brings the numerical solution closer to the analytical solution. But it requires, of course, it requires a smaller time step. So yes, and that's how and epsilon 0 is an epsilon parameter in this dictionary. The next problem I added to demonstrate the two-dimensional case. So it is a popular case of asymmetric dam break. The problem statement you can see, for example, in this article, and so results is also in good agreement with other numerical schemes. So the development is still in progress, and I plan to develop a new solver for two-layer shallow water, but I don't know how to name it. Of course, unfortunately now RSWE-form is available only via my own repository in GitHub, but in future I hope that we will add this to our laboratory repository, so to release it via QGD solver framework. Maybe in future we will add passive scalar transport in shallow water, and of course it will be better to adapt OpenFOAM for the OpenFOAM, the real cases, and run them. So if you have found this project useful or interesting, maybe you can download or visit my own GitHub repository, or hear the command to clone only the branch with shallow water RSWE-form solver, or you can visit our website, Telegram, or repository of our laboratory. So thank you for your attention. I will happy to answer your questions now.
Okay, I think we're 2 minutes over time. We've got 3 minutes for questions, but I don't see any questions yet. My question would have been, so basically, this is strictly shallow water on a plane, or is this be used on a curved surface as well, the solver?
It is a good question. To clarify this, yes, it is a shallow water on the plane, but here we have a variable bathymetry that can define the bathymetry or topography. Here you can see it's better to show it via the picture here. So we have the variable b. It is a bathymetry, so it changes the curvature of the surface, but via the function b. So actually this is the plane surface, but we have the function b that defines the curvature of the surface.
hearing anybody. Is it me or is this? I think my. Hello?
Hello, yes.
Yes. Okay. So yeah, thank you for your talk. We're going, if there are no more questions from what I see, can you quickly answer on the other presentation, or are you aware, because there was a question whether the solvers in the previous one were appropriate for underwater acoustic problems? Do you know anything about that, or should? No.
Maybe Matvey can answer the question.
Yeah, I don't know if he's still. Yeah.
I'm here. I think it can be used in the same way as it can be used PisoFOAM or other solver with Lim acoustics library, for example. So we need a source of acoustic waves, which is just vortexes, and we can simulate the source with a QHD approach or with Piso-like approach. And we need some propagation utility like Fox-William Hawking.
Okay, thank you. Okay, so the next speaker that excites me very much, that is Mr. Tom. The next speaker is Mr. Tan Tri Nguyen from Ganot Computing, and he speaks about a green computing solution for computational fluid dynamics. Please, the screen is yours.
All right. Hi, everyone. Can you see my screen and my presentation? Just to be sure. Well, hello. Thank you again and for coming to this presentation about finding a solution for a green computing solution for computational flight dynamics. Just to present. Sorry. Can you see me now? Perfect. Just to present myself quickly, I am Tan Tri. I work for Cardiff Computing, which is a green cloud computing provider here in Paris, France. Prior to Cardiff, I work on the aerodynamics of a vertical takeoff and landing aircraft for urban mobility. And I have a master in aerospace engineering from the École Polytechnique de Montréal. So as some of you may know, there's a lot of environmental challenges today in the world. It is known that we have to limit the impact of climate crisis, we have to keep the global temperature increase below a certain threshold. And the Paris Agreement sets that objective at 1.5 degrees. For that reason, a lot of industries and governments are putting a lot of efforts into fighting the climate crisis. Maybe some of you even worked on fluid dynamic simulation that were used to reduce the carbon emission of engineering designs. So let's talk about all this today. Because it is digital, it doesn't mean that it's green. The impact of technology is often understated today because it is so widespread in our lives. Like me, I guess you all work on computers, you all have smartphones, maybe at home you all watch TV shows or play video games. And furthermore, the infrastructure that is used to power all of this technology is often invisible to our eyes. And by infrastructure, I mean the cell phone towers, the underwater internet cables, or the servers in data centers. Even for CFD, many calculations are sent on clusters that are far away from the user. So it's becoming less and less obvious what are the impacts of technology. It is not like boarding a plane and knowing it has produced X amount of carbon. The impact of pollution from the numerical sector is becoming a growing concern. Today, it makes up more than 4% of the global emissions, which is more than the aviation industry. It's funny because we always talk about how it is kind of bad for the environment to take the plane, but not about how we use the technology. Those global emissions, carbon emissions, are growing about 9% per year, which is not insignificant. To produce all that technology, there is also the use of rare metals, which are extracted at the big energy cost and can lead to ethical problems as well. And what about CFD in all of this? As you all may know, CFD uses a copious amount of computational power. Large calculations today are run on clusters with thousands of cores. Some of you may say that the hardware today is becoming more powerful and more efficient, but that leads to a vicious circle. The more powerful and more efficient hardware creates a rebound effect and opens the door for even larger computational loads. Today, the calculation are already big with meshes with hundreds of millions of cells, and we are already using more precise solvers like LES. To put that into perspective, let's take the example of one rotation of multi-stage compressor, which was done by Surfax here in France. For just one single rotation, that was roughly 1,250,000 hours of computational time. That is equivalent to more than 14,000 kilowatt hours of energy and more than 4 tons of carbon emission. To give you an example, those 4 tons of carbon emission are equal to 9 flights between Paris and New York. So how can we measure all of this? Well, there's a key metric in data centers that is called the power usage effectiveness, or the PUE, which is the ratio between the total facility energy and the IT equipment energy. In other words, it shows you how much additional energy you have to spend to make your data center work. On the right, you can see the evolution of the PUE across the years as an industrial average. While there were a lot of improvements at the start, which is a good thing, there are also stagnation, especially on the couple of last years. But the PUE is only one part of the equation. Even if you could have a PUE of 1, that means that you have to put the same amount of power as what the IT uses to make the data center work. For an example, here in France, the data centers use more than 14,000 gigawatts hour of energy per year. With the PUE of 1, that is 14,000 gigawatts hour per year of energy that is wasted if it is not recovered. As an alternative, there's another metric that is called the energy reuse effectiveness, which takes into account the energy that is reused. What can we do to lessen our impact? Well, we can adopt a concept called digital sobriety. And here are the key points. First, we can use renewable energies, but that is not always possible because that is depending on the location. Here at Carnot, we try to use solar energy as much as possible. We can all use more powerful and more efficient hardware, but that comes with the point that you have to use that hardware for as long as possible. We can also optimize. So optimizing storage could be as simple as deleting an email that is not used, to optimizing your code to make it run more efficiently. We can also develop in modular ways and make use of open source software. If someone or a team develops something and makes it open source, well, other people can use it, and they do not need to use precious resources to redevelop the same thing. Finally, you can reuse and recycle and create a circular economy. For example, the 14,000 gigawatt hour of energy of data centers per year in France, they could be used to heat more than 16 million showers for people. Here at Carnot, we are trying to tackle the last point with 3 solutions. The first are numerical heaters, which are what this name sounds like. So it's heaters that embed processors and heat homes for the people living on them. There are also digital boilers, which are connected to the water circuits, and the heat from the processor heats the water that is used for cooking and taking a shower. Finally, there are computing racks, which are put in unused space in warehouses, and the heat from those computing racks is used to heat and preserve the food and other goods. All of those 3 solutions have one key point is to put the heat where it is needed. As a result, there's no data centers that need to be built, and there's massive reduction in energy consumption and carbon emission. There's an intelligent orchestrator called the QWare that dispatches the calculation loads where the heat is needed. I won't go into too much detail here, but if you're interested, we have a training on Thursday about how to use OpenFOAM on Carnot's cloud computing platform. We really believe in, yes.
2 more minutes.
We really believe, okay, perfect. Really believe in open source software. So that's why we use extensively OpenFOAM and Pariu for fluid simulation. As a result, you can see what the solution brings to the table. On the left, you can see there is massive energy reduction from not needing energy to heat and to cool. And on the right, there's up to 78% reduction in carbon emission from not needing to spend that energy. For the user, it's also good because the price can be up to 2 times lesser because we don't need to build data centers and we don't need to maintain them and cool them. In the end, the point is not to stop everything. You can maybe use digital sobriety in your lives and maybe not change a smartphone every year or not send a lot of pictures of cat pictures, but we cannot stop everything because some things are useful and some things are even mandatory. For example, engineering solutions that are used to reduce the fuel consumption of aircrafts and vehicles, well, is pretty good from the environment also. So what we must do is think differently, think outside the box, and do things differently because our planet is finite. So we have to find better ways to produce and consume. And thank you.
Okay, thank you very much. That was 16 seconds faster than you had officially timed. Yeah. So you said you're doing a training with the details how to use that on Thursday, right?
Yes, exactly. On how to use the platform to run OpenFOAM simulations.
Okay. Which operating system do you use underneath that?
We use Linux and we use Docker technology to deploy our applications, to deploy OpenFOAM and Pariu. So it can be compatible on all sorts of hardware, and it's easier to deploy it.
I'm looking, but there seem to be no more questions. Yeah.
All right.
So
perfect.
how big is your company? Or was this slide before? Yeah.
We're still a startup. We're around 60 person right now, 60 employees, and we have been here for around 10 years.
Okay. Yeah. Thank you very much.
Thank you.
Yeah. Yeah. I think we'll wait 1 minute with the next speaker, so that people who might come from other sessions, so that we're exactly in sync. The next speaker is going to be Mr. Tom James from Angus Limited. He is speaking about something that interests me very much: how to make our build times 10 times faster. I'm not sure whether this ties in with the previous talk, because it's also whether it's also 10 times more energy efficient. Yeah.
Effectively, yes. We end up doing less work in the end. This talk, it's quite noisy here, and my internet is sometimes quite patchy, so this talk will be pre-recorded.
Okay. That's fine. So you'll hold to the 10-minute threshold, I guess.
Yes.
Yes. Okay. So then thank you very much. So Mr. Tom James about being 10 times faster, and please start.
Hi, my name's Tom, and today I'll be talking about how we made our builds an order of magnitude faster. I'll start by setting the scene before talking a bit about some usability improvements we've made, and I'll finish up by giving you some data on just how much faster our new build system is. Before we start though, I am going to set off a build. So on the left hand side I have a clean copy of Helix Core. You'll notice there is no platforms directory. So if I go time emake all. Okay, so I joined NGIS 2 years ago as a C++ developer, not an OpenFOAM developer. I had to spend some time at the beginning learning how to use wmake, which is the OpenFOAM build tool, and since then I've spent much more time writing an entirely new build system using CMake. Helix Core, which is the NGIS CFD software, partially based on OpenFOAM technologies, is now built entirely with CMake, and wmake has been deprecated since Helix 3.3.1. So what is CMake? CMake is not a build system. It's a build system generator developed by Kitware, who you may know from their other software, for example, VTK or ParaView. It's the de facto industry standard C++ build tool. Most modern C++ projects, including those from companies like Google, Facebook and Netflix, either use CMake or supply an interface to CMake. So that's enough background to get you started. Let's talk about some usability improvements that we've made for the new CMake build system. Because CMake is so ubiquitous, there's loads of useful tooling available. It's very easy to swap out front and back ends in CMake, and we will be doing that actually later in the talk in order to benefit from third-party tooling. So to an extent, users can pick and choose their own workflow. Regardless of how you want to use CMake, it comes with some really nice workflow improvements. The new workflow actually gives us some of the most significant efficiency increases, but these can be hard to measure, so I'm just going to touch on 3 of the most important ones here. The first big improvement is that our build order is automatically defined. In essence, CMake takes the information you feed it and builds a dependency tree, which it then uses to decide the build order on the fly. This means that you can build, for example, a single solver and be confident that all of its dependencies are also built and up to date, and that the solver will work. The dependencies are actually looked after so reliably, you don't really have to clean your builds anymore, so you end up wasting a lot less time building things you don't really need. The second thing is that there's now one and only one place where compilation settings are stored. So I can send you a single text file which parameterizes my whole build, and you don't have to worry anymore that I might have some script somewhere that's interfering and breaking things. This makes builds much more robust and easier to reproduce, and it means that you can spend less time troubleshooting and more time writing code. The last big workflow improvement is this extra configuration step. This may actually be the biggest efficiency improvement in the whole system. Before you can build with any CMake system, you need to configure CMake and generate a build system. In Helix Core, this configuration step takes 3 or 4 seconds and includes loads of tests. We test for simple things like, is your CMake syntax correct? And we test for really complex stuff as well, like, does your compiler support the flags that you've chosen? Or does the third-party library that I found satisfy your requirements? Now there's some stuff I can't test for. Fundamentally, you still have to write valid C++, and there's not a huge amount I can do about that. But I'm aiming to catch literally every single other build bug in this configuration step. If I've got it right, it should take you 3 or 4 seconds, which is how long it takes to configure. It should take you 3 or 4 seconds to find out whether your build is going to succeed or not. Now, let's draw some graphs. The data I'm about to show you comes with some caveats. All these tests were done on my desktop, and I haven't really tried to control the tests very carefully. The results you will see may differ wildly depending on your setup, but you're going to see similar trends. Let's start with the basics. This slide compares a normal wmake build to a bog standard CMake build. CMake with a make backend might be slightly faster than wmake. This is probably on the edge of what we consider significant for these tests. But it's quite easy for us to do better. As I mentioned, it's trivial to swap out the CMake backend, so let's swap out make for something a bit more performant. Google have developed a tool called Ninja Build, which is essentially a cut-down version of make. The Ninja Build homepage explicitly states that Ninja is designed to work with tools like CMake, and it's designed to run builds as fast as possible. However, this doesn't really help us with our full build. It looks like the make backend was actually doing a really good job. However, Ninja's still a really useful tool. It lets us do no-op builds essentially instantly. No-op builds are builds for which no real work has to be done. Developers do this all the time. We compile something, then we rerun exactly the same command just to check that it's worked. That second run is a no-op build. CMake tends to do no-op builds every time it traverses the dependency tree, so although we've not really reduced our overall build time very much, Ninja is still really useful. So let's try and focus a bit more on that overall build time figure. We can break the build down into two parts. The first part is compilation, where your compiler takes C++ files and generates machine code from them. This machine code is stored in object files. And the second part of the build is linking, where your linker stitches together object files in order to create libraries and executables. Now, I'm not going to talk about compilers today, because there are so many differences between different compilers, and even between different versions of the same compiler, that I couldn't possibly do the topic justice. But there's much less choice when it comes to linkers. Normally, Linux uses the BFD linker, and we can easily swap this out for the LLD linker from the LLVM project. With the LLD linker, CMake relinks about 20 times faster than wmake. As a standalone operation, relinking is less common than no-op builds, but it's still not uncommon, so this is nice to have. Unfortunately, the link time is just a small proportion of the full build time, so a full build still takes almost an hour on my desktop. Having optimized pretty much everything else, we really now need to address our compilation time. But I've said I'm not going to talk about compilers. Let's instead talk about Unity builds. A Unity build is when you take your source files and hash include them in big batches into large meta source files. It's a great way to reduce build times because it actually reduces the amount of work that has to be done. Crucially, the compiler has less work to do because headers and templates need to be recompiled less often. This also benefits the linker and it reduces the number of system calls, but the important thing here is the compiler. There's loads more I could say about Unity builds. This is a big change that has very far-reaching consequences, but that's fundamentally what you need to know about how it makes things faster. Before we go any further, I should point out that this is a really aggressive optimization. If you're not already a bit scared of Unity, you probably should be. It's entirely possible to write valid C++ code that is totally broken under the Unity build. So I did have to make some changes in order to get Helix Core working with Unity, but that in itself was worthwhile. I found that Unity was actually a really good indicator of code health. Oh, by the way, turning the Unity build on in CMake is a one-liner. The work is in refactoring the C++ code. If you're going to try building with Unity, you're going to want to have some pretty good tests. But here we are. With a Unity build, we can finally achieve the order of magnitude speed increase in overall build time that we were looking for. This build includes Ninja and LLD, but their impact on the build time is still negligible. All this increase is essentially down to Unity. So that's it, more or less. Let's just summarize what we've done. We've pretty much achieved what we set out to do. All the little day-to-day jobs, be it reconfiguring your build, reproducing customers' builds, or just checking that everything's up to date, these are all orders of magnitude faster with CMake. Since the official release of the CMake build system for Helix Core, supporting customer builds and exotic systems has correspondingly been much easier. And when it really comes down to it, you can build from start to finish in less than 10 minutes. In terms of CMake itself, kitware aren't going to stop working on it. And as the industry standard build tool, future developments from other sources will become available to us quickly and cheaply. And that's almost the best bit. CMake is good now, and it's only going to get better. Before we go on to the questions, let's check on the build we set off at the beginning of the talk. So it's finished. It took 8.5 minutes, and it has built all of Helix Core. If we go and look in platforms, we will find all of the binaries that we would expect to find from a full build. That's it for the talk. So any questions?
So thank you very much for your talk. I don't see any questions yet in the chat. Please people type some questions. One question: you compared the no-op build with wmake with the CMake no-op build, but the wmake build was without something like Ccache, right?
Yes, this is all with all the standard tooling, unless I've otherwise specified, Ninja or LLD. So yeah, you can absolutely improve performance of both systems using something like Ccache.
Okay, but you haven't.
No, that's not it. That's not included in the talk.
Nope. Yeah.
So I think there are a couple of questions. I think they're essentially asking the same thing. There's one about interfacing OpenFOAM with standard CMake-based build and debug interface in VS Code and other standard C++ tools, and a very similar one about interfacing with CLion. Both of these are absolutely possible. We have a developer at NGIS who uses CLion, and a few of us, myself included, use VS Code. And yeah, you get all the IDE functionality that you would expect. So yeah, you absolutely get this integration with all the standard tools. Wow, there's quite a few now. So there's one from Matteo Lombardi. What are the downsides of Unity builds? There's quite a few downsides of the Unity build. You have to be a lot more careful with what you code. If, for example, you have a piece of code that is meant to be local to one file, that tends to get propagated in unexpected ways when that file is hash included as part of one of these Unity files. So you are more limited in the kind of C++ that you can write, but if everything is encapsulated properly and namespaced properly, actually it's not too bad. And the second question from Matteo is, when using the LLVM linker, do you need to use the LLVM compiler as well? No, you don't. You can use ld.lld with either GCC or Clang. I believe it will work with other compilers as well, but I've just tested with GCC and Clang.
Sorry, where do you see these questions? Because I don't see them in the Q&A.
So I have them on the left-hand panel.
Current questions.
Yes,
okay, then my browser doesn't show them to me. Okay, that's a. Okay, please go ahead with one more question. Yes.
Great,
please.
thank you. So there's one from Sergey Lesnik. Have you considered using any alternative to CMake, for example, Meson? Yes, I did consider alternatives. I think CMake appealed because it was so ubiquitous, and I really like handing off a lot of the maintenance work to other companies. A lot of the tools that I have talked about today are developed entirely by Kitware or by some third party, and the maintenance cost so far, I mean, we've been using this for a year or two now, the maintenance cost for us has been essentially nil. We just have to make sure our CMake syntax is valid. I think that's it.
Okay. Funny that I don't see them, but okay. Yeah, thank you very much again for your talk and for your question. this concludes this session. Please, after the talk, go out to the hall and pick up some coffee and then go to the keynote by Herf Yazak. Okay, see you.